In previous videos, we learned that agents increasingly use tools to look up data, execute actions, access files, query databases, and interact with software systems in the real world. But until recently, every platform implemented tools differently. A tool built for one agent framework could not easily be reused in another. This led to fragmentation, duplicated work, and security challenges. The Model Context Protocol, or MCP, was introduced by Anthropic as an open standard to solve this problem. It was first released in November 2024. MCP defines a common way for AI models to connect to tools, retrieve information, and interact with external systems. MCP introduces a standardized protocol between AI applications and external tools. On one side, we have applications such as chat interfaces, coding environments, and other AI systems. On the other side, we have data sources, developer tools, or productivity services. With MCP in the middle, tools become interoperable. Instead of building a separate integration for each platform, a tool can be exposed once as an MCP server and immediately become accessible to many clients. This standardization reduces duplicated integration work, improves security, and allows tools to be reused across different agents and environments. Because MCP standardizes how tools are exposed, a tool can be packaged once as an MCP server and then reused by many different AI applications. In this example, a Google Drive MCP server can be used by an AI assistant, an autonomous agent, or even a desktop IDE, as long as they speak MCP. Instead of writing separate integrations for each platform, the server only needs to be implemented a single time. This reduces duplicate work, makes maintenance simpler, and allows the ecosystem of available tools to grow much faster. The same advantage applies in the opposite direction. When an application is MCP compatible, it can connect to many different servers at once and easily, even if they were built by different people, in different languages, or for different models. In this example, a single MCP application can query a data store server, read customer information from a CRM server, and interact with a version control server. With each server exposing clear tools and data, the model can gather context from multiple systems, reason about it, and take actions, all through natural language. This is why MCP reduces fragmentation. Clients can use many servers, and servers can support many clients without custom integrations. MCP follows a client-server architecture. An MCP client lives inside an AI application, like a chat interface, desktop tool, or agent framework. When the model needs external data or actions, the client sends requests to an MCP server. MCP servers expose three key capabilities: tools, functions that can be invoked, for example, query database, search files, or update a record; resources, a read-only data the server makes available, such as files, API responses, or tables; prompt templates, predefined prompts stored on the server that the client can use to guide the model. The client invokes tools, queries resources, and can request prompt templates. The server handles those requests and returns structured results. This division makes the system modular. Clients focus on the AI task, and servers focus on data and capabilities. Here is what these MCP primitives look like in practice. Tools are Python functions decorated to be callable through MCP. When a client invokes a tool, the server runs the function and returns structured output. For example, adding two numbers or querying a database. Resources are exposed as URIs. A client can request a resource directly without calling a tool. Resources can be static or dynamic if parameters are included in the URI. Prompt templates are defined on the server and returned to the client as ready-to-use prompts. This lets an application provide high-quality prompt engineering without requiring the user to write complex prompts themselves. In Python, all three tools, resources, and prompts are defined simply by decorating functions. These features make MCP servers powerful, reusable, and easy to integrate into AI applications. As mentioned, MCP servers can have prompt templates. Instead of requiring users to write their own prompts, which might be short, incomplete, or inconsistent, the server can provide a thoroughly engineered prompt that allows best practices. In this example, a user might simply type convert report.pdf to markdown. It might or might not work. With MCP, the server can supply a high-quality prompt template that handles the formatting, instructions, and edge cases. This leads to more reliable results, even for non-technical users. MCP servers can also expose resources, read-only pieces of data that the client can browse or query directly. In this example, the application asks to summarize a document, and the server shows a list of available files. Each item is a resource that can be accessed without calling a tool. Resources can represent files, database tables, API resources, or any other structured data that the application might need. They provide context to the model and make it easier to navigate external information during a conversation. MCP also provides a browser-based developer tool called the MCP Inspector. The inspector lets you connect to an MCP server and interact with it directly without needing to write any code. You can list tools, run them, browse resources, inspect prompt templates, and view server logs or notifications. This makes it easier to debug, test your server, and understand exactly how messages are flowing between the client and the server. For development troubleshooting, the inspector is extremely useful because it shows what the client would see, how tools behave, and what data the server returns. So far, we have seen the client request tools, resources, and prompts from an MCP server. The opposite direction of communication is also possible and is named sampling. With sampling, a server can request inference from the client's language model. This means the server can gather logs, metrics, or other data and then ask the model to analyze it, summarize it, or generate next steps. Sampling is useful when sending raw data back to the client would be inefficient, expensive, or a security risk. Instead, the server asks the model directly for inference and only returns the final result. This ability to request inference makes servers more autonomous, and it is one of the features that enables more advanced agent behaviors using MCP. As the MCP ecosystem grows, we need a standard way to discover trusted servers. An MCP registry API acts like a package index, listing verified servers, tracking versions, and reducing the risk of untrusted integrations. With a registry in place, agents can even self-discover the tools they need. For example, if a user asks to find a bug based on my Grafana logs, the agent could search the registry, install the official Grafana server, authenticate, and run the query, all automatically. Dynamic discovery combined with authentication opens the door to agents that assemble the capabilities they need on demand. In this video, we learned that the Model Context Protocol is an open standard from Anthropic that defines how AI applications connect to external tools and data sources. MCP uses a client-server architecture where servers expose tools, resources, and prompt templates, and clients invoke them through a shared protocol. Those tools enable actions, resources provide data, and prompts offer well-engineered instructions. MCP servers can be reused across applications, and clients can connect to many servers at once. Features like sampling allow servers to request inference from the model, enabling more advanced agent behavior.